Okay, so I want to talk a little bit about work, power, and energy here. And how all of these are related, how they're similar, and how they're different, and really just what they mean. So let's start out with the physics definition of work. Now we've touched on some of this before, but it doesn't hurt to just kind of remind ourselves where we're coming from here. Okay, so work is defined as force times distance times the cosine of theta. All right, so just to clear up what's going on there, um, if we were to, oops, let's just fix this. If we were to um, apply a force to something like a box sitting on a surface, okay, say we were to push it and say there was a frictional force acting on this object. So let's just get this all laid out. Here's a person pushing on this thing. Okay, so there's an applied force, and that we'll say is exactly equal to the frictional force, so velocity is constant. We have a constant velocity. Now, this might occur over some distance d, and your force and the direction that this object is moved are in the same plane, so we would just simply say the work done here is equal to Fa, the applied force, times the distance that this object moved, times the cosine of 0 in this case. So the cosine here, right, what we're talking about is just the angle between the force applied and the distance moved, right? It's not hard to believe that maybe, you could slightly switch this scenario around. Okay, and, slightly just change the angle of the force. So it's possible, that's not straight, it's possible that maybe you're going to pull this object, say, like this, right? Okay, so you're going to apply the force something like this. Well, the object is still going to move in this direction, but now my force is up here. So we say it's only the component of force in the direction of motion that we are concerned with, all right? So one way we like to think about that, or to help us think about that, is like it is the shadow of the force cast into the plane of the paper. So you can probably think about that like as if there were a light bulb up here, okay, shining down, and you'd only see, the shadow of the component here, um, right, cast onto the plane of motion. So it's the force here, this component of force, which is F cos theta, right? That is in the same place as the distance traveled. So you can think of it like a shadow being cast on there, okay? So that only because, and of course, if we lift straight up, or we apply an upward force that's maybe not enough to actually move this, then we're doing no work, right? You can apply that force, but we're doing no work. It requires no work to just apply a force. It's only when there's motion involved. Okay, so let's just quickly talk units then. This is measured in meters, and this is measured in newtons. So F times D is Newton times meters. So the unit of work is Newton meters, which we also call the joule. So if you were to break this down to its base units, we've got kilograms, meters per second squared, times meters, which of course translates to kilograms, meters squared per second squared, and that's the base units of the joule. Okay, so just quickly mention power. So this is the rate at which, you can either look at it as at which work is done, or you could also look at it as the, and we'll see why this is essentially the same thing, the rate at which energy is consumed. Okay, so basically you can just do this. P is equal to work divided by time. All right. And so units wise, we get joules over seconds, which gives us the unit joules per second. And this has also been given a name to honor an old scientist, and it is called the watt. I guess maybe engineer. I think Watt was more of an engineer. Um, uh, Designed a better steam engine. Um, just a little aside, sort of interesting because he rated his steam engines in how many horses they would replace, right? Um, so this is kind of where you get the concept of horsepower. So a 1 horsepower steam engine could do the equivalent work that a horse could do. All right. But the nice thing for a farmer in olden times is that you don't have to feed a steam engine, right? It can essentially run, more or less continuously as long as you're upkeeping the fires that run it. And what least, as far as I'm aware, least steam engines to farmers based on what it would cost to feed and keep a horse for a year. So if you could rent a 1 horsepower engine from him, you had to pay him what it would cost for a horse for a year. So you can imagine he got very rich guy, right? You could only lease, you couldn't buy. At least that's what I've heard. I might be wrong on that. Who knows? Okay, so then so then we've got that. That's the rate at which energy is used, and the equivalent that you might be more used to, especially if you're in North America, is the horsepower. It's a similar measure of energy usage. However, it's an imperial system rather than a metric. Okay, so if you go to other places in the world, they don't tell you how much power your car has in horsepower. They tell you in usually kilowatts. All right. It's funny because we're perfectly fine with watts when we're talking about things like light bulbs and kettles, but when we want to talk about a car, it's got to be HPs, and we get all baffled by the concept of watts. But they're measuring the same concept: joules per second, how fast we're using energy, the rate at which energy is consumed. Okay, moving along. Let's talk about energy. And in order to do this, we need to understand the concept of work, energy, theorem, and we also need to touch on the concept of the laws of thermodynamics, and these are related. Thermodynamics. Okay. This is fairly modern in terms of physics knowledge. The concept of taking heat and turning it into work really was only started to be studied heavily during the Industrial Revolution when things like steam engines were being invented, right? A steam engine, a locomotive, or a steam engine in a factory, or really the internal combustion engine that we use today in our vehicles, and even to an extent electric vehicles, right, are turning one type of energy into another. I shouldn't say electric vehicles, that's not quite right. But when we say thermodynamics, what we're saying is we're taking heat and we're somehow capturing that heat and doing useful work with it. So before we lay these down, let's just see what a really simple steam engine might look like so we can get an understanding of how heat is related to work, right? And then we'll go back the other way and see how work is related to heat. And then, go from there. So let's imagine that we build ourselves a fire out of whatever, coal or wood, whatever, doesn't really matter. And we can put that fire under some sort of vessel, okay? And we'll fill the vessel with water. And after some time, that water will begin to boil, okay? So we're taking heat and we're using it to boil water. All right, well, that's going to cause the pressure inside here to build up, right, and get higher and higher. And what we could do is we could put a little chamber off of here with a valve, and we could put a piston inside here, okay? So a piston is basically just, a heavy slug that's able to move back and forth. oftentimes connected to some sort of rod, okay, that is then attached to a wheel. So we could do, say, something like, oops, that's not what I want. Something like this here. Okay, attach that to a big wheel, big heavy-duty wheel. And just make that a little bit longer. So the idea is this, right? You put a little vent right here to make this sort of more automatic. You say, you know, open up the valve and you allow the steam to rush in here once this is boiling, right? You open up this valve and the steam will rush in and pressurize this part, right? This is under high pressure. You open it up, it's going to pressurize this. Well, now this is able to move, right? So that pressure can apply a force in this direction over a distance. So what we've done here is we've taken heat and we've, through a convoluted system, allowed it to do work for us, right? Apply a force over a distance. Now you can imagine, right, what would happen is this would begin to spin around as the piston moved back. And once it got past this little opening, you might blast some steam out. If you've ever seen an old steam train, they tend to do this, let off steam. Of course, this would be regulated by pressure valves. You don't want to overpressurize this because it could go boom, which is not good. But basically, you get this going, right? And you have sort of a self-sustaining engine here now that is going to slide back, relieve pressure, come forward as it gets repressurized. And, you know, if you're a clever engineer, you can make this work. You can then tap into this through pulleys, gears, belts, however you want, and you can now make this do work for you in some other way, right? You can make it like, you know, lift water out of a well or drive an elevator bringing ore up from your mine shaft or whatever you want, right? Now you don't have to do this with animal power or human power. You're just burning and doing work from it, right? So the whole concept of thermodynamics is how do we like put math on all of this? How do we design and engineer these things to be better and more efficient and so on? And then how do we describe really what's happening? How is it that I can burn coal or a log and do work somewhere else? So then the concept of energy comes into this whole system, all right? So the first thing we'll talk about is this. One, and it's the first law of thermodynamics, and that is just simply that it's the conservation law, okay? So energy in a system is conserved. Okay, and if you want that in like ELI 5 speak, you can just say it in the same terms as conservation of mass. No energy. And I realize we haven't said what energy is yet, but just we'll get there in a minute. No energy is ever gained or lost in a system. Okay? And we can add a little addendum on that. It can be changed to other forms. Okay? If we just analyze our system, all right, I'll let the cat out of the bag here, and I'll just define energy to begin with here, okay? So we're just going to say, what is our definition of energy back here? And energy is just this, the potential to do work. So energy is the potential to do work. Or if you even want, you can say the stored potential to do work. So these logs or this coal or whatever contains energy. It contains the ability to do work. And if we're clever, we can find a way to access it and make it do work for us. All right. So we just say there's energy inside here because, you know, if we're careful and clever, we can make that do work for us. And you can see some energy transfers happening here, right? We go from the chemicals and the molecules inside wood. So we'd say there's chemical energy here, right? There's chemical ability to do work. We release it through heat. Heat is another form of energy. It's the kinetic jiggling, the motion of molecules in the air and then molecules in the water, right? And if we jiggle them enough, right, they leap out of here and cause steam. Steam is an applied force in all directions on the surface of a cylinder. So it's actually force per square meter, which we call pascals. force per meter squared. And then that force, if allowed, can act on a distance, right? Which is then work, okay? And then that work can spin this. Actually, I have it spinning the wrong way to lift this up, but I don't know, let's just change direction here. It's spinning this way, okay? And lifting this up, right? So we are now changing the direction. We're applying a force over a distance, right? Because this has weight. We have to overcome the weight, and it acts over distance to lift this object up. So we've got quite the system of work energy transfers here. The first law says, though, whatever chemical energy there was stored here will always be present throughout the system. So whatever amount of energy we have here will be equal to the amount of work we can do here. However, okay, in real life, energy will be lost along the way to unusable forms. It won't disappear, but we won't be able to take all the energy that's stored here and lift with it. Okay, can you see why that might be true? Where might it go? So we would say that there's, in a system like this, an open system, there's lots of inefficiency. Okay, so efficiency is just the idea that, what percentage of the stored energy here is actually going to be able to make it through our system to do work over here, okay? In real life, there's no such thing as a 100% efficient machine or system, or energy transfer for that matter, okay? And we're going to lay that down. That's actually the second law of thermodynamics. But where would we lose? I mean, well, light takes energy, so if we can see it, that's energy that's not going into boiling the water. If we stood by here, there's heat going off in all directions. So you can't really direct heat in one specific, direction. You could insulate it and so on and so forth, but it's going to get into the sides of this container and out into the environment. So right here, you're not able to transfer 100% of the energy available into the boiling water, okay? Then, of course, there's things like friction, right? All these, objects that spin and turn and run and slide experience friction. So to overcome that friction on the push and the pull, some of that energy has to go into that, okay? And that often manifests as heat, right? Heat coming off the side of all of these things. As these belts are running, there's friction in these systems, and we're losing here and here, right? Okay, and so for all those reasons, you cannot ever have a 100% efficient machine. So efficiency would be, if we have 100% in the coal, how much actually comes out the other end? I don't know, maybe in this system, like 50%. We would say then that if there was 1,000 joules of energy used here, we might get 500 joules of work over here. Okay, so this would be a 50% efficient machine. So that leads us to the second law of thermodynamics, which just basically says in any system, some energy is lost to unusable forms. Okay? Some energy lost during energy transfer. Okay? So the above are the first and second laws of thermodynamics. So energy is conserved. In other words, we're not making it or destroying it. But the second law says there's no such thing, basically no such thing as a 100% efficient machine. You're transferring one type of work into energy, or one type of energy into work, or one type of energy into another type of energy. Some will be lost to the environment. All right, there's no such thing as a perfect system. We often, when we're doing physics, ignore this and say, in a perfect system, what would happen? But you just have to realize that in real life, there's no such thing as that. Okay, so these are the laws of thermodynamics, and then work energy theorem is just this. It's kind of like related. Work energy theorem. You can theoretically do an amount of work equal to, okay, so a system, I shouldn't say you, a system is capable of doing an amount of work equal to the potential energy that it contains. okay? And that's ignoring the second law, right? Because really it can't do all that because some will be lost. And then we'd say um, a system is capable of storing potential energy equal to the amount of work put into it. So let's do an example of this, okay? Let's do an example of where a system might be able to store energy, where we can do work, store energy, and then get work back out, okay? And we'll talk here now about one specific type of potential energy, and that's gravitational potential. So we did discuss this like very briefly when we were learning about work to begin with. But let's say there's a ball at the top of a hill. Now we can get it up there one of two ways. We can roll it up the ramp or we can lift it directly up. So let's say, just to start off here, that we lifted it directly up, okay? Ooh, I don't like that. We lifted it directly up, straight up here, okay? Okay, so we're just going to change our nomenclature a little bit, but we'll say that the work that we did, to lift this up, must be equal to the force of gravity, but in an upward direction, right? So we have to counteract gravity by applying an upward lifting force. And if we exactly counteract gravity, there will be no acceleration of this ball. It will just move constantly, right? If the net force on it is equal to 0, it'll move at a constant velocity, okay? So the force we have to apply is equal and opposite to the force of gravity, right? So we got to apply, now that's not weight anymore, that's work, Fg, okay? So we have to apply Fg times whatever height we have. Now we're going to lift in this direction, so no cos theta necessary. Okay, so FGH, and FG, of course, is equal to mg, okay, h. So the amount of work we did is equal to m times g times h, all right? Now what that also means, according to work energy theorem, is that when we have a raised object with mass, all right, that contains potential energy. We actually would say then that this has Eg, E being energy, G being gravitational, equal to mgh. What just happened there? Okay, equal to mgh. Okay, so think about that then. If this ball were allowed to roll down the hill, okay, it would come to the bottom with some velocity. Okay, that might then be able to do some work for us somewhere else, right? So if we had like a big nail sticking out of the wall, you can imagine that this ball with velocity could strike the nail and drive it in, applying a force over a distance, right? So the work we did here sits in potential energy, just sits there, right? It'll just sit at the top of the hill until it gets that little push it needs, just that little tap. That, you know, gravitational potential energy gets converted into what's called kinetic energy, the kinetic energy of motion. We'll look at that in a minute. That then rolls over here and drives in a nail, okay? In a perfectly efficient system, the exact amount of work we put in to lift this is then available to do work over here. None would be lost in that system, okay? So this is the first type of potential energy. You have to work to get it, and that is that. What's going on here? Some strange stuff's happening. Work can be converted into Eg, okay? And then we'll just define Eg, and that Eg is equal to mg times h, okay? So any raised mass can do work for us, okay? An example from real life is like hydroelectric power. If you have a dam here and you have water behind the dam, and you allow that water to flow through the dam, as the water rolls downhill, you can extract electrical energy from it via turbines, okay? So the potential to do work in raised water is what allows us to get hydroelectric energy, okay? So that's one example. Now let's take another example here, because we know that the ball gains some velocity, right? And clearly, when it's down here, it has no more gravitational potential energy, right? The gravitational potential energy is gone, but it's stored in a different way now. That potential energy is stored in the motion of the mass. So we're going to look at how that works. So to kind of derive out how we deal with that, let's imagine that you have a large ball on a surface and that you begin to apply a force to the ball, okay? And now we're going to imagine that we're friction free just for ease. Now this has a big mass. You are applying a force to it, and that force is acting over a distance, right? So the work that you're doing on here is causing this ball to gain velocity, isn't it? Okay, so let's look at our formula. Well, force is actually made up of two things, isn't it? M and A. So what we get is we actually get MAD. The work we're doing here is equal to M times A times D. So the mass of the ball times its acceleration, which came from the force we were applying, over some distance. And what will change about the ball between then and now is that here it'll have a velocity of, say, 0, and sometimes later it will have, some higher velocity, a velocity higher than 0. Does that make sense? If I apply a force to an object and there's no counteracting frictional force, this object will gain velocity as I push on it over a distance. Makes sense, right? Nothing crazy there. This will also, though, since I did work, store potential energy in the motion of the ball. Since there's no friction, none is lost. The amount of work I did here must then be contained in the motion of the ball. And you can imagine, like in our example, that a heavy mass that's moving can do work. Okay, so therefore it must contain potential energy. So now this isn't very useful, right? We want to know something about the ball in terms of its actual velocity and its mass. Well, mass is there, but let's see if we can just do a little bit of work and fix this. So we know this, right? Right, that's true. At the start of this, we said that the initial velocity was 0, so we can just get rid of that. Okay. And we can just do a little rearrangement here, and we could say that v squared over 2 equals AD, right? And then we can do a little substitution. Where we see AD, we can put v squared over 2. So, just a subtle change here. Since we did this work, and now we're done, and we've got a rolling ball with mass, and we've stopped pushing on it, the kinetic energy, the energy of motion, equal to the work we put in to make it roll, should be equal to m, which we already had, times v squared over 2. Now, this is not the form it's usually written in, so we'll just do a slight change. We would say that EK is equal to 1/2 mv squared. And take it back all the way. That is the amount of work we did to get the mass moving to begin with. Okay, so if we want to know the potential energy of a moving mass, we have this formula to help us out. Okay, the interesting thing about this is that increasing velocity adds energy exponentially. All right, increasing mass only adds it linearly. We'll do a couple of little examples about that. Before we do, I want to talk about springs. That will be the last type of potential energy that we need to study for right now. And let's just talk about how those work. So springs are interesting. I think you'll see how you can store energy in them. If we have a spring, and we compress the spring, we are applying a force over a distance. And you can imagine if I compress a spring and I say put a little ball on it and I release the spring, that could send the ball zinging off, right? Or even really, it could just like do work for us back out, right? It can apply a force over a distance to say push a box along a surface or something like that. So springs can store energy. The work we do on a spring stores energy in the spring, okay? Now we did a little experimenting with springs and we found this to be true. So we would say that the change in length of the spring, we call that delta x actually, right? That's the kind of nomenclature we used. The change in length of the spring was delta x. I mean, it's a similar idea to d. It's just that we're talking about a change now, okay? And we found this. We found that the change in x was equal to some value k times force. Okay. This is the spring constant. And what units is it measured in? Newtons per meter, right? I don't think sorry, I wrote that backwards, didn't I? My bad. Just fix that. Sorry, it should be like this. There we go. That's better. My mistake. Force equals kx. That's a better way to write that. My mistake. I apologize. Okay. So what we're saying here then, right, is that force is proportional to the change in x, right? The more force we apply, the larger the change in the length of the spring, right? Force varies though, it increases as we push farther, right? In other words, to shorten the spring to this level, you apply 10 newtons. To shorten it to this, you apply 20 newtons, say, right? So you have to like adjust force. So it's not just as simple as constant force times d. This force is changing depending how far along we've pushed it, right? So we're not going to just get F times d as the amount of energy stored in here, because the amount of force increases as the spring gets compressed or stretched, actually, okay? So F equals kx. So my mistake. Let's just fix this. This was the spring coefficient. It is a characteristic of a given spring, right? The more stiff the spring, the higher this value becomes, right? The more force we have to apply to squash it a certain distance, right? Think of the difference between a very light watch spring and the spring on a car shock absorber, right? The car one requires a lot more force, and therefore has a higher K value. This is measured in newtons per meter. The change in X is in meters. Okay, those would cancel out and we get a value in newtons. So let's just graph it quickly and see what it would look like. So you have done this, and if we put force on the y-axis, which newtons per meter would say that we want to do, and we put delta x here, you would find that you get a linear relationship, okay, at least for part of the spring. If you overstretch it, you get something weird happening, but during the stretching, you get this linear relationship, which is called Hooke's law, the Hooke relationship for a spring. And the slope of this, then, the slope is the K value. Okay, so this would be a stiffer spring here, right? You need a lot more force to move at a certain distance, and this would have a lower K value. Okay, so the K value is measured in newtons per meter. So now I want you to look at this. We've got force here on your y-axis, and we've got distance here on your x, right? So let's just clean this up a little bit and figure out how we're going to figure out what the amount of work we did was. So if we've got force here and we've got distance here, then force times distance should be the amount of work that we did, right? So the work should be the area under our spring graph, right? Our area under our spring graph, all right? So I'm going to do a little bit of changing here. Now, we said before that F was the equivalent of K times X, and it's nice to know our work done based on the spring constant. So if that's F here on the y-axis, well, if it's equal to Kx, we can just do this. So how do I find this area then? Well, we just need to change this up a bit. Instead of force, we'll put K delta X in there. So we've got K delta X, right, times X, right? So we've got a Kx times X, and since it's triangular, we need half of that. So the area then bounded under here, which is the amount of work we did, right, for a spring, we should get it equal to Kx squared over 2. Okay, so that's the amount of work we had to put in to compress the spring, and therefore E sub S, sometimes called EE, depending, should be equal to 1/2 Kx squared. All right, so to summarize, potential energy in terms of raised masses is found as mgh. That's the amount of work that you had to do to raise the mass, and therefore that's the amount of stored energy that can be pulled back out as the mass returns to a lower height. Oftentimes, if you're rolling a ball down a hill, all right, that mgh might be converted or changed from gravity to kinetic energy of a moving object. And then that could further be, say, converted into elastic potential energy or spring potential energy as 1/2 kx squared. So these are kind of the three reservoirs, if you want, of mechanical potential energy that are fairly common. Now, there's other places to store potential energy, like in chemical reactions, for instance, in nuclear reactions, and so on and so forth. But mechanically, or in a mechanics unit, these are the main places. Okay, there's possibly some other ones, but these are the mechanical places to store it. So let's see if we can figure out a little problem here. Say we have a system like this, and we do this, a little spring at the bottom, and we put a little mass at the top. Okay, say this is 5 kgs. Let's say this is 10 meters high. Okay, let's say this is position A, this is position B, and this is position C. Okay, and let's give this a K value, this spring here, a K value of 400, let's make it 4,000 newtons per meter. Okay, so what we're going to say here is that we're going to expect some energy transfers to happen. All right, we're going to roll the ball down the hill. That gravitational potential energy that it has here is going to be converted into kinetic energy first, right? So when it's here, it has Eg. When it's here, it has Ek. Okay, and when it's fully compressed, the spring, it has Ee. So we're going to have an energy transfer from one kind to another through this system. And we're going to kind of be able to keep track of that with like sort of a little graph, right? So let's draw this little graph, and we'll say that in point A, if this represents the total energy of the system, right? This represents the total. At the beginning, we have Eg, we have the possibility for Ek, and we have the possibility for Ee. Okay? At the beginning, all the energy is located in terms of Eg. There's 0 Ek, it's not moving, and the spring is not compressed at all. So at the beginning, at point A, we have a graph that looks like this. Then we release it. So let's call this point like I. So it's like halfway down, right? Halfway down, it's got some velocity, and it's lost some Eg, right? But it hasn't lost all of it, and it will be going faster later when it loses more Eg. So let's talk about point I. So point I has a graph of total energy that looks a bit different. Now the total overall energy of the system has not changed, but the forms of it have, right? So now what's happened is we've lost some Eg, right? We've come down a little bit. The H is no longer as high as it was, and that is change has been sort of converted, if you want, into Ek. The total energy, the sum of it all, though, still equals the total system. Does that make sense? No energy has been added or taken away. It's now just spread between two forms. See, it's rolled down. Okay, now let's continue on to point B. At point B, it's completely lost all of its Eg, right? It's at the lowest point, it's in its ground state, but it's now rolling as fast as it will ever roll in this scenario. So the Ek of the object now is where all the total energy of the system is located. Okay, then it comes in contact with the spring. And let's say it hasn't fully compressed the spring, it's just partially compressed it. So we'll call that point 2, where it's partially compressed the spring. Okay, so when that happens, it's not completely slowed down. It has 0 Eg. It still has a bit of Ek, but now it's also got some spring potential energy. Okay? And then finally, at point C, it's totally, completely stopped. The spring is maximally compressed. It has no more Eg. It's got no Ek because it's not moving. And all of that initial energy is now stored as potential energy in the spring. Okay? You can imagine in a perfect system, no energy is lost, you know, and let's like just say that it just barely gets to the top of this hill. It would just continue like oscillating back and forth forever and ever and ever, wouldn't it? Okay? So the way we think about this then is that the E total of the system, E total, the total energy of the whole system, should be equal to the mgh at the maximal height. Okay? That's the total energy of the system, right? We had to do work to load the system with energy by lifting this ball up here to begin with, right? So whatever work we did is the amount of energy that's available in the system to do other things, right? That also means then, you know, that at point B, the E total is now equal to 1/2 mv squared, okay? And then at C, the E total is equal to 1/2 kx squared. But what about the in-between times? Well, what about at I? Well, at I, the E total is in two forms. It's in mgh prime, whatever height it's at now, plus what? Plus a little bit of kinetic energy, right? So the way you could say that is you could say it's equal to whatever remaining Eg we have plus whatever Ek it's gained, okay? It's not all here and it's not all here. It's somewhere in between. But what is the same is the total energy. It's always the same, no matter what, okay? And then at point 2, here, that E total is now spread between Ek and a little bit of Ee. So a little part of each of these, right? So some 1/2 mv squared, whatever is remaining, plus 1/2 kx prime, right? Because it's not fully compressed, squared, okay? So this is kind of the energy transfer, and we can now make things equal. And we have numbers, so we can solve problems, okay? We don't have enough information to solve I and or solve Roman numeral 1 and Roman numeral 2, but we could say the total energy of the system is equal to mgh. In this case, we have a 5 kg ball. It's under 10 meter per second squared gravity, and it's at a height of, what did I say, 10 meters. So we could say then that this system at any time will always have 500 joules. If we know that, we can then solve for other things. And we can make all of these things equal to each other at different points in the system. The mgh to begin with will all become the 1/2 mv squared later, and it will all become the 1/2 kx squared at the end.